Okay, welcome to our last video in the Exponents and Logs series. This one has specifically to look at some applied problems with exponential or logarithmic functions. Specifically, we'll look at population growth, interest compounded continuously, and exponential decay. First off, we need to look at the formula that drives most all of those examples. And this formula will be different than ones that you've seen before. The interest with when you have compound interest sort of looked like this: P of t is equal, or I think we had A is equal to how many you start with. So often that was P, and then 1 plus some interest rate raised to some kind of an exponent like that. Notice that this one's a little bit different. And a main component difference is this E, or the number E, being the base there. And with that base E, it allows us to make a simpler formula than this other one. Now, keep in mind that this one is used for population growth or compounded interest, or interest compounded continuously, not semi-annually or annually. It's interest compounded continuously. And we can also use one almost identical for exponential decay. So in looking at the formula, this is the population, or the amount after a certain length of time. This is the amount that you start with, so the P0. E is our base, that's the number E. K would be our population or interest or whatever the rate is. And finally, T is time in years. And we'll use this formula in looking at those three different examples. First off, let's start with population growth. Here's an example. In 2001, population of India was 1,030 million. That'd be about a billion. And the exponential growth rate was 1.4%. So first they want us to find the exponential growth function. To do that, substitute all the variables except for t. They want to know what the growth function is with respect to t. So let's do that. So population after a given time, we don't know what t is, so we just write that. Population that I start with is 1030 million. Let's just express things in millions. So it'll be 1030. E to the k, our interest rate is, or our exponential growth rate is 1.4%, so that's k, so that'll be 0.014 times t. So that there would be our exponential growth function, plugging in everything except for t. I should have but here. Now, if they wanted to know what the population was in 2007, I could simply plug that in. So the time between 2001 and 2007 is 6 years. So the population after 6 years is equal to 1,030 million E to the 0.014 times 6. Let me do that on my calculator. And I come out to 1120.3 million people. So instead of 1,030 million, after 6 years there will be 1,120.3 million people in India. Now the last question says, after how long will the population be double? Well, that's, I guess if I'm starting at 1030, to double that would be 2060. But notice that what happens in the formula when you're solving it is, if we're doing this question here, to solve it is population after a given time is equal to how much you started with times e to the kt. So it doesn't really matter what you start or end with if you're wanting things to double. If I were to write, I guess I'm starting with 1030 and ending with 2060 is equal to 1030 e to the growth constant we know, 0.014, and they're saying how long, so t is what we're looking for. Notice that if I wanted to solve this, I must isolate the base that has the exponent there. So I'm going to be dividing both sides by 1030. And what do I get when I divide both sides by 1030? 0.014t, there's a decimal right there. When I divide these two, I just get 2. 2 is equal to e to the 0.014t. So when they ask for how long before things are double, you can put the initial and what the final one would be, but certainly when you divide those two, it'll always come out to 2. Now, to solve this, I'm looking for the value of t. I could, since it's in an exponent, I could change from exponential form to logarithmic form. I choose to use the property of logarithmic equalities, which means I'm going to log this side and log this side. Since this is base e, I'm going to ln this side and ln this side. Okay, using the power rule, I'll bring that out front. So I'll get 0.014t times the ln of e is equal to the ln of 2. Ln of e we know is just 1. So I really have 0.14t is equal to the ln of 2. Dividing both sides by 0.014, I should get the time it'll take before India doubles in population. Let me do that on my calculator. I get 49.5 approximately. So in about 50 years, the population of India will double if the growth rate stays at 1.4%. So that's an example then of using this formula to help me solve an exponential growth rate question. Here's another example using compounded interest. So an interest compounded continuously, that's sort of a key word. If it doesn't say continuously, I might have to use a different formula. But if it's continuously, I can use this one. And it's the same game. This will be the amount after a specific time, the amount that you start with, the interest rate compounded continuously, and the time in years. So the question says 2,000 is invested, that'll be here, compounded continuously. It grows to 2983, that'll be this, and it does that in 5 years. Interesting. So they ask us what the growth or what the interest rate is. So they gave me everything except for k. Alright, let's plug those in. P of t is equal to P0 e to the kt. I always like writing my formula down. The amount of money after specific time is 2983.65 is equal to, I started with $2,000 times the number e raised to the k. I don't know the interest rate, but I do know that it was in there for 5 years. Now you see that this question is set up just like the one we did before. To solve for k, it's in the exponent. I must isolate that base. So we'll divide both sides by 2,000. I'll do that on my calculator. And I get 1.491825 is equal to e to the k times 5. Okay, in the exponent I have a variable. 2 ways I can do this. I can change from exponential to logarithmic form, or I can use the property of logarithmic equalities. Just to change things up, I'm going to change this to log form. So the exponent, 5k, is equal to, we'll use ln, or we can use log base e of 1.491825. So that's just changing from exponential form to logarithmic form. Notice I've got a 5 here. I'll have to deal with that later. I know that log base e is the same thing as ln, so I have a button on my calculator that I'm going to be able to do that with. I'll figure out what the ln is and then divide both sides by 5. I'll do that. And it comes out to, when I divide by 5, 0.08 and then a bunch of zeros after that. So my interest rate then, that I'm compounding this continuously, will be 8%. Boy, if I could get money like that at the bank, I would take it. So now it says find the exponential growth function. The growth function would be the same function as the start, and I'd plug in everything except for time. So it'll be the amount of money after a specific time is equal to how much I started with. Started with 2,000. E to the k, k is my 8%, times t. That would be my exponential growth function. Then it says, what will be the balance in 10 years? Okay, I just substitute in a 10 and then multiply it all out. If they say, how long will the initial amount be doubled? Then I'll do the same thing as I did before. Maybe I'll do that one. If I want to know how long until it's doubled, I would say, well, to double my 2,000, I would get 4,000 is equal to 2,000 times e to the 0.08 times t. Again, to solve for t, I must isolate that part of the term, divide both sides by 2,000. Now solving for t, again I could change from exponential to logarithmic, or I can ln both sides, whichever I want to do. I'm getting good at that change into exponential form, so we'll go 0.08t, that's my exponent, is equal to log base e of 2. Or 0.08t is equal to the ln of 2. So I'll do that on the calculator. Ln of 2 divided by 0.08 equals. So my time is going to be 8.66 years. That won't take very long for my money to double from $2,000 to $4,000. Okay, so that's an example then of interest compounded continuously. I can use the same formula as I did in the other one, and the same sort of game applies, that I plug the numbers in and then solve. And notice that we'll always be having you solve for one of the exponents there, forcing you to change from exponential to logarithmic, or to log or ln both sides. The final example today is on exponential decay. Notice I can use the same, it's not exactly the same formula, except there's a minus there. So if I'm doing exponential decay, the formula is the same except for the k value is minus. And that makes sense because it's going smaller. So our example of exponential decay is with carbon-14. It has a half-life of 5750 years. In other words, to go from, say, 50 grams down to 25 grams, it would take 5,750 years to do that. So the percentage of carbon-14 left can be used to determine how old a particular material is. So in looking at the Dead Sea Scrolls, archaeologists said that there were 77.7% of its carbon-14 remaining, and if it is, then how old was the linen wrapping? Well, first off, one of my problems here is I need to figure out what the exponential decay rate is, that k value. I don't know what that is. But do I have information that I could determine that? It says it has a half-life. So if it starts, say, at 50 and ends at 25, it says the time it takes it to do that is 5750 years. So I can use that information right here in the first part to come up with a k value for carbon-14. Let's do that. So, and it doesn't matter what numbers we use here, 50 or 25, 100 or 50, as long as this one is half of that one. Why don't we use 1 and 2? So P of t is equal to P0 e to the minus kt. So let's start with, say, 2 grams, and we would wind up with 1 gram because it's a half-life. E to the minus k, I don't know, but it says that it takes 5760 years to do it. Again, in solving for k, or a variable that's in the exponent, I have to isolate that part. We'll divide both sides by 2. So I'll get 0.5 is equal to e to the minus 5760 k. I just sort of changed the form a little bit. Now, change to exponent or to logarithmic form if you want. We're getting good at that one again. So this would be minus 5760k is equal to the log base e of 0.5, or minus 5760k is equal to the ln of 0.5. I'll do that on my calculator. And I come up with k being equal to 1.20 times 10 to the minus 4. If you're not too familiar with scientific notation like this, we can also write this as 0.00012 times 10 to the minus 4 just means move the decimal 4 places to the left. So 1, 2, 3, 4. There. So my K value then for carbon 14 and its decay rate is 0.00012. So if they say that the Dead Sea Scrolls have 77% remaining, then I can go and I can determine how old they are, or I can figure out what their time was. Here's my formula. Pt equals P0 e to the minus k times t. So they're saying they have 77% left. So if they started with 100%, now they're at 77.7%. E to the minus k, I just figured that out, 0.00012 times time. And I would solve this one just the same as I've done all the other ones. So I need to isolate this part. I'll divide both sides by 100, so I'll have 0.777 is equal to e to the minus 0.00012 t. Change to logarithmic form, so it'll be negative 0.00012 t is equal to log base e of 0.777. Log base e is the same as thing as ln. Let's do all the calculations on the calculator. And it comes out to 2102.6 years. So we would say if the Dead Sea Scrolls still retain 77% of the original carbon-14, that we would estimate, give or take a second or two, we would estimate that those Dead Sea Scrolls would be approximately 2100 years old. So today we've looked at 3 applications, and we've used these formulas, notice they're very similar, to look at population growth. We've looked at interest compounded continuously, and we've also looked at exponential decay. Again, in solving for any of these things that are, any variables that are in the exponent, we'll be forced to either change it to logarithmic form or to use our property of logarithmic equalities.